Thank you everybody for coming. I will be talking about survey and measure development, obviously in R. Okay, so a lot of what I'm going to talk about is the theoretical underpinnings and all the methodology behind why we would measure things via a survey, but still try to keep focus on R. I'm going to try to not get too philosophical, and then provide a few resources. So I think I heard a couple people know some things about this. Are there social scientists in the room? Okay, we have one. Okay, so I'll try to speak to a various range of audiences here and really try to focus on applications in R. Okay, so I put everything on RStudio Cloud. If you can write down that URL, you can go in there and that's gonna have everything. I don't know, is everybody aware of RStudio Cloud? Okay, if you aren't, if you've ever used RStudio, it's a cloud version of that and it's free, you can go on, so that will have everything. You don't have to worry about dependencies and whatever, it'll just do it for you. So you can go there, check that out. Okay, so, all right, can everybody see that? Some of these images, I'm not sure. I can try to zoom in. Is that better? Okay, cool, great. Okay, so what we're going to talk about is measuring consumer behavior via a survey. So there's a whole area of social science research that goes into this, and whether you're in psychology or marketing or nursing or really anything social science related, this is a whole area of expertise, and you could do a whole dissertation on this. So I'm just going to do the greatest hits of this and really focus on how to crunch some of the numbers in R. So for this example, I just totally made this up. Let's say we wanted to measure something like website quality. So we're an e-commerce retailer and we wanted to see, how do people like our site? So we might come up with something like this. This is a pretty short one. A lot of times these have a lot of answers and items and things like that. But just for purposes of being able to fit on slides and things like that, I just made this a lot smaller. So we have our survey here. Each of these prompts we're going to call items. We're going to call a scale of 1 to 5. I think everybody's filled out a survey like this before, and you may have heard of the Likert scale after its originator. It's usually going to be 1 to 5, doesn't have to be, but we're just going to stick with 1 to 5. That's the most common. And then finally, we're going to call this an instrument. So why we call it an instrument is the same as we would call a ruler or a scale or something an instrument, right? We can measure things over and over across different subjects at different points in time, and we're still going to get the same results. So there's a lot of stuff that goes into this. It's not as simple as just taking a ruler and measuring somebody's height. This is what we'll find is a latent construct that we need to measure indirectly via these items. So we'll get into all the steps on how that's done. You may have seen this 2x2 used before in various contexts. In our context, we're going to hit on 2 key concepts of measurement, being reliability and validity. So talking about measurement, if you had something like a scale or a ruler, you would hope that you could just keep on using that instrument, you get the same results over and over. This is the same concept here. So what we want is down there on the lower quadrant, we want something that's both reliable and valid. So reliable being that it's consistent, that we keep getting the same thing, and then valid being that we're actually measuring what we intend to measure. So if we have an instrument that's measuring website quality, but it's really measuring like customer satisfaction or something, maybe we don't want that. Maybe we're measuring something different than we're claiming to measure. So I'm almost going to get to the code here. Here's just all the theoretical underpinnings. And we've probably all seen a flowchart like this using data, and we know that usually it kind of goes off the rails, but we have a nice flowchart, an iterative process here of how to develop a survey. So we'll start with item generation, then we'll have to actually send out the surveys, and then we'll go, this is more of the data intensive part that we'll really more focus on. You heard of things like factor analysis, structural equation modeling. We'll get into kind of the highlights of that. And then as you'll see, validity and reliability, we're kind of doing that throughout the process. So there's no one way to measure that. This is something that we're concerned about throughout this entire process. Okay, so I think finally we have some code. So I just did a binge of all the packages that we're going to use, and then I'll call them later on so you'll actually see what function is related to what package. So some of them might be familiar, maybe some of them aren't, but we'll see, how I'm using them. Okay, so the first thing I'm going to look at is item generation. So unlike maybe some data that you're used to working with, we actually have to create this instrument ourselves, right? We're not going to just scrape it from the web or go to a database or whatever. We actually have to make the server ourselves. So before we do that, we want to make sure, is this something worth even measuring? Because it takes a lot of effort to send data to people. If we're getting garbage in, garbage out data, why even send the survey out in the first place? So there are a few ways to do this. I'm going to focus on the second here, content validity, how essential is each item to the concept, but there's also integrated reliability. So do experts agree this is a good item? So I'm just going to keep it simple. Let's say we have 2 experts, and we want to get a sense, is there any agreement on whether this is a good item? So the really simple way, and I just have 2 experts rating their assessment of items on a scale of 1 to 3. We have pretty simple structure here. I'm going to use this agree function from IRR. That is going to show that there is a 61.5% agreement, which is pretty good. Seems like there's some shared agreement of what people think is a good item. The problem with doing that is we're not accounting for things occurring just by chance. So we're going to use Cohen's kappa. This is coming from the psych package, and we're going to use the psych package a lot for doing this. So welcome to psych. Cohen kappa, we're going to get some output here. Basically what we're doing is adjusting our scale of agreement due to agreement just happening due to chance. When we get that, we have some interpretation here. And can everybody see this okay? Yes, okay, great. So here we want to look at the weighted kappa. We have an estimate of 0.32. That's actually not great. So looks can be deceiving at first if we're just using raw agreement. That might not be the best way to do it. So there are various measures on actually making sure that we have good items before we even get any data. So this is before we actually do any data exploration. We're just designing the survey. Okay, the second thing, I'm not going to spend a lot of time on this because this is all important stuff, but you don't really do it in R, so you have to go out and collect the data, right? So you have to think about sampling, you have to think about bias, and it's important stuff, but it's not done in R, so I'm just going to keep going. Okay, so I call this step 2.5 because it's not really on the flow chart, but obviously it's important. So actually exploring the data when it comes in. Again, we're going to use psych a lot for this. First one I'll do is describe. This is a cool function if you're not familiar with it. It's just a nice way to get descriptive statistics. It's one of many options, but I like this one because you get some distribution statistics here and everything's nicely arranged. The problem with doing just descriptive statistics with this, of course, is we had people measure their responses on a scale of 1 to 5. So, a mean of 3.5 or 3.53. Nobody actually responded that way, so this isn't really helping us. We already know what the range is, right? Hopefully it's 1 to 5. I didn't really get into how you clean all the data and all that stuff. I just figured there are a lot of resources on doing that, so I'll just focus on the interpretation of this data. So this is a nice function, but not really what we want. One that's a little more helpful is with our psych package again. We can use this response frequencies function. So this is actually going to give us discrete frequencies for each response. And then I just cleaned it up a little so it's easier to read. So here we can see, each item, what % of the respondents responded, 1 or 5 or whatever for each of our items. So now we're starting to see a little story about how each item was responded to. That's not what I want. Okay. Excuse me. Okay. All right, so that's great. It would be great to get a visualization of this too, so I'm going to use Lightweight package here. We need everything converted to a factor, and I don't know why this is happening. Anyway, we need everything converted to a factor, so we'll do that. I'll just do mutate if from dplyr, and I'm just going to change the names of this so we can actually see the entire item as it's read rather than just the item description, so a little more context what we're measuring here. Okay, so I'll graph that and just put in some arguments and things like that, and zoom out a little bit so we can see. All right, that's pretty much everything. Okay, so now we have a nice visualization. We have the response frequencies for each item. We're getting a good picture of how people on average kind of responded to each of these items. But this is still not really what we want. And I just printed these items here for more context. Because what we really want is to measure something outside of these items. Like, it's great to get everybody's response on each of these items, but we're really more interested in website quality. So none of these in themselves are directly measuring the quality of the website. We want to measure some kind of outside latent force that we can compose into different dimensions. And you'll see that we'll find 3 of them here. So we want to measure something kind of outside of the items in themselves. And really how we're going to do that is, oh, go ahead.
I'm sorry, can you tell me the name of that link to this work again?
Oh yeah, I wish we had like a whiteboard or something. Is there a better way to, can I broadcast that anywhere? Do we have a way to write it somewhere? Or I'll just write it on like a piece of paper maybe and send it around. I was thinking of, I don't know, I was thinking of putting it as like a footnote or something, but I didn't do that. Okay.
I tried to remember the 6 digits, but no.
All right, I'll write this down.
Because I was saying, I could just post it on the meetup.
Oh, that would be good too.
Oh, yeah.
Okay, so between the 2, I think that should be good. Cool. All right, I'll just put this with the white. Okay.
Thank you.
Oh, sure, yeah, that's okay. Any questions? Everything good? Everybody see this making sense? Okay, cool. Great. Okay. All right, summary statistics. Okay, so we visualized this. Now, so what we really want to find is the underlying structure of this data, because we want to infer or see what dimensions of a latent variable are reflected in the data. So first thing I'm going to do is just print the correlations. We'll start from there. This is kind of another nifty one from the psych package, lower core, because you get kind of a nice correlation matrix where you're not doubling up on all your values. So that's helpful. I also want to actually visualize this, because then this will really start to tell the story of what's the underlying structure of this data, what dimensions might be reflected in this survey. So I can use core plot for that, and we get a nice correlation matrix here. I'll try to zoom out a little bit. That's annoying. It goes up to the top of the page when you zoom out. I didn't know that. Anyway, so we have a nice correlation matrix here. It's kind of a nice heat map. We can see how every item is related to the other one. This is kind of, oh, go ahead.
What's the size of the circle?
The size, I believe it's doing both the intensity and the size are to scale, if that makes sense.
Correlation. I see that it's also heat map color and size correlation. Okay.
Yeah. I'm sorry.
Absolute value or something.
Yeah, so I'm just doing that I think these are all positively correlated. That's something I didn't really get into, is that it's easiest to interpret this if every item is kind of, if all the items are positively worded versus negatively worded. So if one's like, I do not like this, and the others are, I like, you want to reverse it so they're all on the same side, and then it'll just be easier to interpret it later. So these are all positive correlations. These ones are stronger, and I kind of cheated with this just to kind of tell the story of what we're going to do here. So we want to find these patterns in the data, and we'll do this formally with factor analysis. But right now, I just want to show, visually, how do we see what items are kind of more related to each other than others. So that's going to be the focus of our factor analysis. So we have this group here, we have a group here, we have a group definitely here, and then if I keep scrolling, there's one that seems to kind of lay on its own. And again, I'm kind of cheating a little bit, but you'll see if you actually read through these items, there's going to be a reason why. Like, you'll actually understand why some of these items might be more related than the others. So we'll get into how to actually empirically derive that and then actually formally test it. Okay, so that's what we're going to do now. So we're talking about factors or dimensions. So this is dimensionality reduction. We're not doing principal components. We're doing factor analysis because we're more interested in measuring a latent variable than actually just composing this down based on the variance. So how many factors or dimensions are reflected in the data? Do any items not reflect a factor? So those are going to be the 2 things that we do, and we'll actually do both of these in this step. Okay, so now I'm going to do exploratory factor analysis. I'll use tyke again for this. I picked 3 factors because that's kind of what we saw. There's a lot of rules of thumb on how to do that, so I'm just going to stick with 3 and we'll keep going. So this is a pretty simple function here. FA, digital quality is the name of our data set, and then I'm just going to print out the names just to show you that this is not like, you just pick a number and you move on. There's a lot of different criteria and ways to interpret this, so I think there's at least 50 here. We're just going to hit on the top like 2 or 3. But there's a lot. All these psych packages you're going to see have a ton of output, and we'll kind of walk through how to do that. Okay, so the first thing, this is the most important thing. We'll look at the factor loadings. So this is basically like the correlation of each of these items with the latent dimensions. And there are a lot of rules of thumb on this. Again, I try to keep everything simple. So I just said greater than an absolute value of 0.5. Some people might say, it should be greater, like 0.6. It might depend on sample size. So there's a lot of different rules of thumb. I just wanted to keep this kind of as simple as I could. And then I didn't get into, like, you'll see some of these items have 2. So like this one has 2.2 and this one has 0.5. So that's called a primary factor loading, which is fine as long as it's low, like less than 0.3 or something. So you basically want every item to load onto one and only one factor strongly. And if it has a crossover, that's okay. So these all seem to be okay, except again, I kind of cheated and put this one at the bottom. We have 1 minus 0.1, and we'll see a little bit further why that might be happening. But it looks like most of these are good. They're loading onto one and only one factor, and they're loading pretty highly. Okay, so then we'll look at the eigenvalues. This is more of an old school way of doing this. So basically the rule of thumb, and it makes sense, your number of eigenvalues greater than 1 should be equal to the number of factors. So it's not like you're losing any information kind of when you are doing the factor analysis. Again, we can just access part of the output here with e.values. And it looks like we're pretty close. But this one is right on the brink. So again, it's kind of telling the story that maybe there's something kind of contaminating our model and not it's not telling us about the factor like we want it to, or the variable. And this is kind of the same way of doing the same thing. So if you've seen a scree plot before, and let me try to zoom out again. All right. So the scree plot is basically a visual inspection of that. Our y-axis is the eigenvalues. Our x-axis is the number of factors, and we want to choose something below the elbow. So you see the dip in the elbow. Basically, you're going to pick 1 below that, and that's just a nice visual way of showing how many factors are probably in this data based on the eigenvalues. And then finally, I'm going to do ones a little different. So I'm going to take the factor scores and correlate them. The reason that I'm doing that is, again, we want our items, all of our factors or dimensions should be related but not too related. So if they're like really high, they might be measuring the same thing. In that case, we can just combine them into one. So these look okay. So these are just all different steps, and no one of them is the take it or leave it way to do it. If any of them would be, it'd probably be factor scores, but you still want the context. You're still getting bits of information from all these other ways. Okay. All right, so we did have a result that wasn't great. What happens then? Well, let's just go back and look at the data. So the last one was the one that we had a problem with. The website provides good hours. I don't know what that means. Is it the reps have good hours, or the website doesn't have much downtime? I don't know what you mean. So that is not a good item. I don't know what that's about. So we should get rid of it. And that's partly why we did all the steps at the beginning, was to get, eliminate chances for things like this. Okay, so I'm just going to drop it from the data set. I'll just do a simple select function here. And I'm just going to call this digital quality 10. A lot of the times when you're working with these instruments, they'll be named like something and then the number of items or the number of variables in the scale. So I'll just go with that notation. And then we'll just rerun everything and see, did that do what we wanted to? I just ran it all by 1, indexing that, and so that item's gone. Everything looks good. I'll just keep going. The eigenvalues look okay now. These look okay. So that seemed to clean it up. So it looks like there's some bearing in the data that we can that three factors are reflected in this data. So now what we want to do, well, before that, I stuck this in here. So coefficient Crobox alpha. This is showing, again, we look at reliability and validity as many times as we can throughout this whole process. So this one shows, do similar items in the survey produce similar scores? So if you have a survey item that's measuring something that sounds very similar to another item, people should rate them similarly, right? So like if you rate a 5 for one, it should be, you know, so that this is basically what we're testing here. I'm going to look at the standardized alpha from this. The problem with Crobox alpha is it's sensitive to the number of items in your scale. So the more number of items you have, chances are you're going to get a higher Crobox alpha. So this helps standardize and adjust for that. And we have a standardized alpha of 0.1. And I'll just keep scrolling here. Anything between 0.7 and 0.9. If it's higher, you might have too many items that are multicollinear, so you can drop something. If it's too low, then that means that things aren't reliable. So drop items or rewrite them, do what you have to do. So again, kind of this takeaway that a lot of the stuff we're doing in measurement, you want things to be related, but not too related. They should be similar but not the same, distinct but not different. So that is one way to do this reliability. Then I put another one in here, split half. So this is the same thing. Basically, we're trying to say, you know, if we take our survey, we split it into two data frames, basically by columns, just split the columns randomly in half, and we correlate the scores. Are we going to get some, are they correlated? So is each half of the survey kind of helping to tell the story of this construct? And it appears that it is greater than 0.8. We have split half, 0.81, that's the same score that we had for Crobox alpha. So they're very similar in measurement. This one's not as common because if you're measuring more than one construct in a survey, you're not going to expect to get split half reliability because you're measuring different things. So usually Crobox alpha is what you're going to see. And last but not least, just to draw a picture of this, so if you use FA diagram, we'll get a nice picture of what we're doing. This will be helpful later on because some of the models that we draw are going to get really convoluted, so it's just the beginning. But we can see, you know, we have each of our items, here are the factor loadings, here are the correlations between the factors, so we can kind of get a nice visual picture of what we actually just did. Making sense? Everything good? Cool. All right, so now what we're going to do is actually formally test what we just did. Okay, so confirmatory factor analysis. So we're right here in the middle. And if I keep going. So we did EFA, and that's an empirical investigation of explaining the relationships in the data. So we just wanted to empirically see, you know, what kind of factors and patterns can we find in this data. So it's part about kind of theory development. So now what we're going to do is actually formally test. So we're really kind of throwing the dice down, and we're staking a claim in what we think this data should model to. It'll be a hypothesis test, it'll be a chi-square test, but there'll be a big caveat to that about whether we can actually fit our data, our model to the data. Okay, so to do that, I'm going to use this lavaan package. It's a clever acronym for latent variable analysis, and it takes some getting used to with the terminology. It's kind of weird to how you define models in lavaan. But basically what we'll do is use that equals tilde terminology there to assign items and factors, and then we'll fit the model to the data. That's okay. All right, so yeah, that was my good slide too. That's okay. Okay, so just to make this easier to work with, because there's going to be a lot of typing of variables in lavaan, I'm just going to rename all the columns and then call up lavaan. So now we have our model that we're defining here. So basically what we're doing is we're in control now of saying that I think these items should load to this factor. And I'm just calling them F1, F2, F3 for factor 1, factor 2. You could name them the dimension if you wanted to. Just for simplicity, I just F1, F2, F3, and then you see the equals and the tilde, and then you see that we're adding those items together. So we have our defined model now. And now what we're going to do is fit the model to the data. So to do that, I'm going to use the CFA function. We have our data and our model. Those are the only two arguments there. And then what I can do is summarize our results. models. So if I call the summary, I'm going to include standardized measures and fit measures here. And just like everything we've been doing, there's a lot of output. The first thing that you're going to see is chi-square, because formally this is a chi-square test. We want to see if our data, if there's some more than what would be expected at random or by chance of the model fitting the data, or the data fitting the model. So I'll just keep going. There's a lot of output. We'll explore this a little bit later. And now my fun slide. Okay. So the problem with doing this is that chi-square is sensitive to sample size. So a lot of the times we're going to see that there is a significant result when there really might not be. So there's a lot of other ways that we actually want to test whether we have a strong measurement model, and we're actually formally checking whether we do. Okay, so a few of these, we have comparative fit index, Tucker-Lewis index, and then RMSEA. First two over 0.9, third less than 0.05. I'm just going to focus on the absolute fit measures. So there are other ways. You can do a nested comparison. You can use relative measures. I'm just more familiar with using these absolute measures. So when you're comparing or looking at a measurement model, look at these statistics. These are going to adjust for the sample size, so you don't have that problem with chi-square. So these are going to be a lot more common than just reporting chi-square. Okay, so we can do that. I'm going to use the fit measures function here, and that appears to be good. They are all over or under our standard for RMSEA. So it looks like we have a strong fitting model. So there's, we formally tested that, yes, there appears to be, more than just chance would have to say that this model fits well. Okay, so one thing that I did want to point out, this is usually not really an issue, but just it's good to know. We're using a maximum likelihood estimator for this. So normality is assumed, and if you want to check that, you can do the Marty's test here with the Marty function in psych again. And it looks like we do have a problem with normality. What you want to do in that case, you can use other estimators. Yes.
Sorry, every time we go into that, so you have like Likert scale. All your data is 1 to 5, right?
Yeah.
And you have a bunch of columns. So that's just what do you make a plot per column, or are you somehow summarizing all of this data for that? Plot?
Yeah, for a multivariate normality.
So you say you have like 12. How many rows do you have? Don't you have like?
I think I have 10 items and then a couple hundred observations.
Okay.
Yeah.
Maybe for one or.
Well, this is going to do a multivariate normality, so I don't know the whole complexity of how you do the axes, rotations, and all that stuff to get to that. You could test all of them independently. I just did a multivariate test here. So it appears that there might be an issue with normality. If that was a problem, you can use the MLR estimator. So what we'll do is use robust standard errors that are going to try to adjust for that non-normality. And now what we're going to get is our measures using maximum likelihood, and then we'll use the robust standard errors. So yeah, if we're looking at chi-square, maybe there is a change in our p-value, but we're going to try to go with these other fit measures, and we can see here that the robust CFI, robust TLI, they still look good. So, I mean, if you have a really small sample size, this would be something to look into, changing your estimator for fitting the data, but that's, usually not a problem. So I just put that in there just as a caveat. Okay, so we'll keep going here. All right, another thing that's just nice, a nice feature here. So if you're reporting this data and you just want to access various elements of our fit, if we do call standardized solution, we'll get a nice data frame that's very helpful for just slicing and dicing and getting the data that we want. So here, I just want to report all of our estimates in a nice, tidy data frame here. And so that's just another good one to know. Okay, another good one, we can get factor scores out of our models. So this is very popular for clustering. If we wanted to do some kind of customer segmentation or something like that, we could take our factor scores and find patterns in those factor scores. So essentially those are going to show the relative standing of each respondent on each of these 3 dimensions of our factor. So predict means compute. It's not really predicting anything. but we can just get that into a data frame. I'll do the describe function again, and then this is just another little life hack from Psych that if you can do this multi.hist function here, and then you get a nice histogram of each variable in your data set, so you don't have to do any iterations or anything. It'll just do them all for you. Okay. So now we're going to get back into the plotting. Spaghetti and meatballs is often what people call this structural equation modeling, because as you'll see, you've seen before and you'll see again, there's a lot of lines and circles and things like that. So if I use this SEM paths function here from SEM plot, we have another picture of what we did, and it kind of does look like spaghetti and meatballs with the lines and the circles and everything. But it's very helpful because you can actually see, so these models can get pretty complicated. I'm sticking with the just basic measurement. And we'll get a little bit into actually how to use this model for a predictive outcome. But this just kind of tells us sort of visually of what we're doing. Okay. All right, so one other caveat here with construct validity. Again, we want things that are similar but not so similar. So this is convergent validity. So dimensions are similar but not the same. Discriminant validity, dimensions are distinct but not unrelated. So it's the same idea that each thing is kind of telling a unique aspect of our latent factor, or of our latent variable. So to do that, I'm going to use this reliability function from SEM tools. I can get the average variance extracted greater than 0.5. Composite reliability greater than 0.7. We'll use this avvar and omega functions here, or output. And if I go down here, really they should be a little bit higher. So this is 0.47, and then this one looks okay, but some of these dimensions don't look as good. So what's happening here is if you have something that's fitting well as a model, but you're getting lowish reliability, it could mean measurement error. In this case, it's me going and fidgeting with all the data to get the numbers that I want. So we do have measurement error, and that's probably why we're getting these results. Okay, step 5. That's so we just did convergent discriminant validity. We are also going to do concrete validity. So now that we have a model that empirically seems to have some bearing, that we actually tested formally, we can start to use this measurement model to interact with the outside world. So if we wanted to correlate this with other items, other variables, or do linear regression, which is what we're going to do, we can, now that we know that we're actually measuring what we think we're measuring and it's reliable, we can go out and test what's called the concrete validity. Concrete being that this has some basis in explaining some outside phenomenon. Okay, so for example, I just came up that our website, we really want people spinning out the rewards points. So I think, did I have that down here? Yeah, I do. Okay, so we really want people getting their rewards points. So let's say that they've been accumulating them for 6 months after taking the survey. Can our measurement model be used to predict this dependent variable? Does it possess predictive validity? So we can actually test whether we can use our measurement model to explain some kind of outside variable. So we are going to scale everything and standardize it now because this data is not on a scale of 1 to 5. So if we just standardize everything, that'll help with stability and interpretation and all that stuff. And I just, I love describe functions. I had to get it in there again. Okay. All right, so now what we're going to do is actually run a regression. Again, lavaan kind of has its own way of doing things, but in this case, it'll just be like regular R. So we assign our tilde, we can plot our y against our x's, and we're just putting this on top of our measurement model. So basically what we're doing is defining f1, defining f2, defining f3, and then we're going to say, can we use this measurement model to regress rewards points? And then we'll just fit the model to the data. I just use the SEM function. It's the same estimators. I just prefer using SEM versus CFA because we're really doing more of a structural equation model now than a confirmatory factor analysis. But you'll get the same results. And then I'm just going to include the R-square here. So we'll get our standardized measures, fit measures, and then the R-square. So we'll get the same kind of results in the output. The model fit isn't really going to change. It's still really good. And then I'm just going to keep going. We can get our fit measures here. So here we can get our estimates. Here's our p-values, our z-scores, etc. Everything looks very strong. And our regression, here's our actual regression on each of those factors. So those look pretty good. And then we have our R-squared. So we're really focused on the variance explained of the rewards points. So that's 0.75, which is pretty good. It's as good as dummy data is going to get you. So now we're seeing that we can use this model to predict outside variables of interest. We could correlate this with another item or another phenomenon, and it could be another measurement model. It could be some outside. It doesn't have to be a latent variable. It could really be anything. If everything's standardized, and you can do that. Okay, so just to kind of drive that home. If we rotate our model here, it just makes it easier to read. So I'm going to use this SEMpaths function again. And I'm going to include the standardized coefficients so we get a more comprehensive look at what's going on. So this kind of looks like what we might be used to. We have our items. They are reflected in these three factors, and then these three factors. So if you're seeing these arrows, it kind of means something that these are kind of feeding into rewards points. These are feeding into our items, and this is our measurement model with predictive validity. Okay, so last but not least, replication. There are a lot of different ways to do this, just like all these other steps. So one way we might want to test is among the same population or the same respondents even, does this test seem to hold up over time? Another way would be, does this test seem to hold up across distinct populations? So if we give this test to people in the US versus Canada or something, does the measurement model seem to hold up? I'm going to focus on this first one because this second one gets pretty complicated. And okay, so this isn't really that common in business settings because it would be really hard to get people to respond to the same survey twice. And it has to be close enough in time that their answer hasn't changed for any outside reason. So if their sentiment or their opinion actually changed on these items, it's okay that they change. But if you're testing something, one day and like the next day, nothing's really changed in their lives or whatever, they should respond the same way. So we have T1 and T2 this time. This is just another advertisement for psych, I guess. Describe by function. This will give us the group descriptive statistics for these variables, grouped by time. So we have time 1, our variables, and then we have time 2. And now I'm going to do this test-retest function again from psych. So define T1, define T2. I just filtered those into the two groups. And then our ID is ID. So you have to have the same respondents. So it would be really hard to do this for marketing or something, to have the same respondents do a survey, a couple days apart. So this is probably going to be more common in, like a hospital or a school or something like that. But, it's still good to know. And then what we'll do is correlate those scores across T1 and T2. They should be pretty highly correlated. In this case, they are. So it appears that our test has some stability over time. So this is like a repeated measures kind of way of testing for the stability. Okay, so I think this is everything that we covered. I don't know if we got to all of these things, but so we have validity here. So these are the 3 C's of validity, just as a recap. Content, we didn't really get into that one. Construct we did, so we looked at the average variance extracted, convergent reliability, made sure that the items or the dimensions are related but not too related, and so forth. And then we did criterion, so we did predictive or concrete. You could also do concurrent, which is some measure at the same time. So if you're correlating items, you could actually correlate two things together. And then we did reliability. So there's equivalence, that the raters seem to have some shared agreement that these are good items. Internal consistency, we looked at that, and now does the survey seem to kind of hold on its own? And then stability, can we test this at multiple points and get the same results? Then we have our flowchart here. Here are the packages that we use. So this is just kind of like a recap of everything that we did. And if you're interested in this stuff, so this scale development, that's kind of the Bible for doing this in an academic setting. So if you want to know all the methodological steps and why we're doing all this stuff, that would be the source for that. There really aren't that many resources on doing this stuff in R. This GitHub page has a lot, so I randomly found that one if you're interested. And then so if you're more interested in just a wholesale approach of using this in a marketing context, this R for Marketing Research and Analytics, I think they just came out with a new edition. So they go into this a little bit, but then they also have like a really more comprehensive view of marketing research. So how does this fit into, you know, clustering like I mentioned or something like that. And if you're on DataCamp, I have a course there as well, so you can practice these different things. And now, if anybody has questions or if your head's about to explode, this would be your time. So, yes?
When you showed the simple statistics using psych, there was one column that labeled MAD, M-A-D. What's that? Right there. Before mean and max, M-A-D, what's that?
Absolute deviation?
Yeah, I'm thinking so. But I'm guessing it's the mean absolute deviation. Is that what someone said?
I said that. I'm not sure I know what it means.
Oh, okay.
I know what it stands for, I don't know what it means.
Yeah. Mean absolute deviation. I don't know.
Let's Google it.
Okay. Darn it.
I think mean absolute deviation will be much smaller than standard deviation.
Did anybody find it? I'm having trouble here. Okay. Mean. Okay. Okay, that's fine. Average distance between each data value and the mean. Average distance. Oh, okay. So that's a dispersion statistic. Cool, thank you. Yeah, it's good to see that stuff. Anybody?
So just looking at the function documentation, though it's not mean, it's this one's median absolute deviation.
Oh, well, that's why you read the docs, right? That's good. Thank you.
It says calculated from the math function from the stats package and core R. Note, by default, it's adjusted by a scaling factor. They'll make it the same size as the standard deviation for normal data, up to be about the same size.
Okay. Yes.
Question.
Oh, yes.
You tested for normality and it showed the curvature.
Uh-huh.
And if you look at the Likert scale, you would expect that the variability at 1 and 5 would be much smaller than variability at 3. So if you use Box-Cox transformation and the inverse sine function on Likert scale, that may straighten it out. Have you tried that? And
Yeah.
will it change dramatically other things?
I'm guessing that would work. I'd have to check for that. Thank you. Yeah, oh, okay. Yeah, oh,
Since you said that there was a problem with normality,
yeah.
after you said you fixed it, it didn't show another normal QQ file afterwards, correct?
Yeah, so I just changed the estimator. So there would be different ways if you wanted to transform the data, but rather than doing that, I just used another estimator here. So this MLR will use robust standard errors and try to correct for non-normality. And it really didn't make that much difference in the data. So I don't know. It's good to know, especially with smaller sample sizes, to use the MLR estimator. And there are a couple other ones. The default for lavaan is maximum likelihood. So there are a couple other ones, and this one is what I used, and then that worked to adjust for non-normality. Yes.
So for your lavaan model, all your original variables like affected the factors. So that case would really make that much. Did you need to use lavaan there to get that? I would imagine that would be better if like you had tons of variables and only a few of them. I guess what's the advantage of doing it that way? It seems like a lot of complexity. Maybe you still have predictive linear regression with those 10 variables in the prediction of reward points.
Oh, so what would be the other option using the?
I was thinking that if you're going to do factor analysis, usually you have tons of variables, and a lot of them don't do anything, right? So you want to try to figure out which ones are important or not. You do a factor analysis or some sort of dimension reduction, get some things that you know predict, and then use those in your model. But all of your 3 factors in your factor analysis are like 0.5 correlated with the original variables, which is really high. So I imagine my guess is that wouldn't make that much of a difference, but I use anyone to correct me.
Yeah, so I think with this example, I kept things really simple, and usually these are going to have, at least a couple dozen items. So in that case, a construct might have, like half a dozen factors, and then that might be a little less of a rigged way to do the regression. I mean, what you could do, especially with something like this where there's not that much variability, you could just take the factor scores and regress the outcome on that, and it'll be like the same results. So there is some stability there, but doing the lavaan model, yeah, it's a lot of work to do that, but depending on the kind of measurement model you have, that'll just give a more comprehensive explanation of the outcome. So.
The survey items you had in was one of the first slides, there was a plot, and I'm just curious what plot it is that has the distribution of the responses or something.
Yeah.
Like a vertical, or you could,
So I did
that.
the Likert package here.
Okay.
Everything has to be a factor for that, and then I just changed the items. So I don't know, does anybody have a better hack for working with labeled data? Because I've never got a good system. Like what I would love to have is the item descriptions as a label to the actual variable name, and I know that I forget the package that does that. I just never got it down. I never got it working like how I wanted. So I usually just have 2 data frames, and that's terrible, but then I could just swap out the names when I want. Because this gives you the entire item description rather than just the variable name, so that and then there's a lot of optional defaults here. If you wanted to shift these around, like right now these are centered at 0, you could center them to the left or whatever, get rid of these percentage signs. So that's nice if you're working with survey data. You can get a response frequency, because that's often what people want to see. So. Cool. Any other questions? Should I go back to the head explosion slide? No, I think it was okay. Thanks for everybody's questions too. It's cool to have perspective from different people on how to do this, because I learned all this stuff in my graduate program at Case, and I was doing information systems design and took a lot of classes with this. So there might be perspectives that I'm not familiar with that are definitely helpful in building a better model here. So cool.
Thank you.
Yeah, thank you. Yeah.